I start to run, I accelerate in a forward direction, which means my final velocity is greater than my initial velocity. Since I'm experiencing a change in velocity, I'm experiencing acceleration. Because I'm accelerating forward, my acceleration is greater than 1. Now I'm experiencing Newton's second law of motion. Net force equals mass times acceleration.
Speeding up forward is just one example of acceleration. We can explore the others by looking at our position, velocity, and acceleration versus time graph. If I'm speeding up or slowing down, if I'm accelerating, my position changes exponentially, which means it changes faster rate than time changes. This is why we get these curves. The slope of my position versus time graph represents my velocity. So here I'm going from a shallow slope to a steep slope. I'm speeding up and I'm going in a forward direction. Here I'm still speeding up, but I'm going backwards. I went from shallow to steep and I'm moving in a negative direction. Now I'm going from steep to shallow, from fast to slow in a positive direction. I'm slowing down forward. Here I'm going again from steep to shallow, but I'm going in a negative direction, so I'm slowing down backwards. All of these curves show you different types of motion, speeding up, slowing down, forwards, and backwards. When we look at our velocity versus time graph, velocity is what's changing here. Acceleration's definition is the rate of change of velocity. Faster is further on my velocity versus time graph. So if I start further, I'm going faster. Closer is slower, and these are individual points on the graph. Above the graph is forward, below the graph is backward. So for example, this is forward speeding up. I started close, ended far, and went slow to fast in an upward, forward direction. Here I'm still going forward, but I'm going from farther to closer. I'm going from faster to slower. If it's below the graph, I'm going backwards. These are all my negative velocities. Negative means a backwards direction. Here I'm going from farther to closer, so faster to slower. I'm slowing down backwards. Here I'm speeding up backwards. I started at that x-axis, so I'm starting at rest, and I'm increasing my velocity as it moves further away. It's backwards because it's below. Then we have our acceleration versus time graph. Acceleration versus time graph, you really have 3 options. If I'm speeding up, I only have 2, or speeding up or slowing down, I only have 2. Above is positive acceleration. Below is negative acceleration. These graphs are going to always be horizontal. It's always based on the slope of the velocity versus time graph. If I had a positive slope on my velocity versus time graph, I have positive acceleration. If I have a negative slope on my velocity versus time graph, I end up with negative acceleration. These are always horizontal lines. Here on Earth, our motion is defined by Newton's 3 laws of motion. The first law, an object at rest tends to stay at rest, an object in motion tends to stay in motion unless acted on by an outside unbalanced force. This represents balanced forces, objects that are moving at a constant velocity, objects that are stopped. Newton's third law, for every action, there's an equal but opposite reaction. This talks about how forces happen in pairs. When I push on the wall pushes on me. When we're talking about unbalanced forces, which cause speeding up and slowing down of objects, we're looking at Newton's second law. This formula, the net force, the difference in force, is equal to mass times acceleration of the object. Let's explore Newton's second law in a little more depth. The net force is the sum of all forces pulling on an object. So if I add my positive forces and my negative forces together, this is my net force. With objects that were stopped and moving at a constant velocity, the forces were balanced, so our net force was 0. The net force has to do with the mass as well. This is in kilograms. This is the amount of matter stored in an object. This is different than the object's weight. Weight is the gravitational force. And then acceleration of the object. This is the rate of change in an object's velocity.
As I accelerate forward, gravity pulls straight down on me. The surface creates a perpendicular normal force on me. I'm applying more force forward than kinetic friction can pull back on me. So I have a net force, or more force pushing forward than pulling back.
The process of creating a force diagram is the same, even if we're dealing with unbalanced forces. Start by identifying the forces. What's pushing, what's pulling. Go through your checklist of all the things that cause the different forces we work with. Then you have to ask yourself, Vertically and horizontally, is it balanced or unbalanced? Should my arrows be the same length or different lengths? Is one force pulling more or the other? There's always going to be, in the direction of our acceleration, more force. More acceleration is in the direction of higher velocities. The force that's bigger points in the direction of that higher acceleration. Calculate those forces then. We can always calculate gravity. We can calculate friction. And then we can use, if we know it's balanced, we can use those values to balance out the force equations. Now, not all directions are going to be balanced. That means that sometimes a left is going to be bigger or smaller than a right. An up is going to be bigger or smaller than a down. When that happens, we're going to find the acceleration. Let's say you have an 85 kilogram object and it speeds up as it's pushed to the right. So we need to figure out what forces are acting on this object. We always have gravity no matter what. It's on a surface being pushed along the ground, so we have a normal force. Something is pushing it to the right. That's my applied force, and it's speeding up to the right, so I know that horizontally it has to be unbalanced. So we're going to have friction pulling away the opposite direction. Unless we know it's a frictionless surface, always assume there's friction. Now that I have my general qualitative force diagram, I can start to calculate other values. Fg is negative 9.8, my gravitational force, negative 9.8 times mass. So I'm going to plug in that 85. That gives me negative 833 newtons. So gravity is negative 833. Vertically, I'm not speeding up, I'm not slowing down. In that dimension, I am stopped. So my forces are balanced. Fg plus Fn has to equal 0. In this case, 833 plus negative 833 gives me a net force of 0. So vertically, I'm balanced. Let's say that we applied 450 newtons forward. 450 newtons are applied forward. Here's a new formula. We can calculate our friction force. If I know my normal force, I multiply by mu, that funny looking m/u there, mu. This tells me how much friction I'm experiencing. Let's say it's 0.5 is my mu, my coefficient of friction. 833 times 0.5 means that we're experiencing 416.5 newtons of friction. And because it's in the backwards direction, it's negative 416.5. My friction force is less than my applied force. These forces are unbalanced. It's unbalanced to the right, which means I'm accelerating to the right, speeding up to the right. Now that I have my unbalanced forces, I can use that net force. My net force is the sum of all of my unbalanced forces here. Forward plus backwards, always going to be one dimension. When I add those together, that's my FA plus my FF. So my net force is 33.5 newtons. What that really is saying is that FA, my applied force, is pulling with 33.5 newtons more in the positive or forward direction. Now I can use Newton's second law. If I know my net force, if I know how much friction is, or how much less friction's pulling, or how much more an applied force is pulling, I can find my acceleration. Plug in what you know. There's my formula. My net force was 33.5. My mass is still 85. I want to solve for my acceleration. I know it has to be to the right, so we're looking for a positive acceleration here. Divide both sides by 0.85, and I get a positive acceleration of 0.39 meters per second squared. And that's reasonable. I'm going forward with a positive velocity. If I'm speeding up, both my direction and acceleration should be positive in a forward direction.
Dynamics helped us figure out my acceleration. I started at an initial velocity of 2 meters per second, and I'm traveling for 12 seconds. Calculate my final velocity.
Once you have 3 givens, you can use the kinematic equations. In this case, you can either solve for an equation and solve using your inverse operations, or find an equation that already uses the order of operations, has the variable by itself. In this case, distance or displacement is not included. I'm solving for final velocity, so the only option is that equation. Always start by listing your given information. We know that we started with an initial velocity of 2 meters per second. We have a final velocity that's unknown, Our distance or displacement is not included. We calculated our acceleration using our force diagram, and we're traveling for 12 seconds. We said that displacement or distance is not included. There's our equation. Start by writing it out. We have our givens. Write out your formula. Substitute into the formula. In this case, our variable, final velocity, is already by itself. So we just need to follow the order of operations. Underline, evaluate, and rewrite. So 0.39 times 12 gives us 4.68. 4.68 plus 2 gives us 6.68. Final velocity, so the unit is meters per second. I found my given information. I identified what was not included and what I'm looking for. I wrote out my equation, substituted in, and solved for an unknown velocity.